Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 9 on modeling with quadratic functions. This is our last lesson in the particular unit on quadratic functions and quadratic relationships, and we're just going to play around a little bit with taking a look at some practical examples of where we might see some quadratic functions in the real world. So let's jump right into it. And let's talk about working with a quadratic model. In this lesson, we will focus on using quadratic models to predict and optimize. Almost always, our solution to whatever thing is being asked will depend on either the intercepts, the x-intercepts of the quadratic model, or the turning point of the quadratic model. Now, one thing we haven't reviewed yet in this unit is what's known as the axis of symmetry formula. So let's just take a look at that from Algebra 1. For a quadratic function of the form y equals ax squared plus bx plus c, its axis of symmetry is located at x equals negative b divided by 2a. So it's really cool. You know, one of the things that you can prove, especially once you have the quadratic formula, is that the turning point of any parabola, and more specifically the vertical line that sort of cuts it into two equal parts, can always be predicted by taking the linear coefficient, negating it, and dividing it by twice whatever the leading coefficient is, negative b divided by 2a. Anyhow, we're going to use that just a bit in this lesson. Let's take a look at exercise number 1. An object is fired upwards with an initial velocity of 112 feet per second. Its height, in feet above the ground, as a function of time, in seconds since it was fired, is given by the equation h of t equals negative 16t squared plus 112t. Letter A. At what height was the object fired? That one's pretty easy. So all I'm really asking for in this situation is what h of 0 is. Why don't you go ahead and substitute 0 into this equation and calculate what height the object was fired at. All right, well, that's actually very, very simple. Because of the structure of the equation, h of 0, which is negative 16, times 0 squared plus 112 times 0, well, 0 squared is 0, negative 16 times 0 is 0, 112 times 0 is 0. So this thing was fired from a height of 0 feet above the ground, meaning that, of course, it was fired at ground level. Okay, let's take a look at letter B. Sketch a general curve of this equation below. All right, and here's what I mean. I don't want you to use your graphing calculator yet. We'll get there. We will, all right? But I should be able to think about what this thing looks like without breaking out the calculator yet. So let's just draw something that looks like this for the moment. All right? Now, we know that this thing starts when t is equal to 0 at h equals 0, which implies, of course, that the point 0, 0 is our starting point. We also know that this is a parabola that opens downward because its leading coefficient is negative, which means that, right, we're firing this rocket upwards and then it's coming back down. So the general form, or the general way that this curve should look is something like this. Now, I don't know its peak height. I don't know when it hits the ground again. I don't know any of that. And all of that we're going to figure out in time on this particular problem. So let's take a look now at letter C. Algebraically, find the time that the rocket reaches its greatest height and the maximum height. Label these on the graph that you drew in part B. All right, well, if we want to find the maximum height of this thing, then what we really need to do is we need to figure out that axis of symmetry, right? We need to figure out where the x-coordinate is that sort of slices our parabola in half. Now, we know that that can be found, and it's t, not x here, by negative b divided by 2a. The b is the coefficient multiplying the linear term, and the a is the coefficient multiplying the squared term. The plus c is, if you will, 0 in this problem. So the time at which it hits its maximum is going to be negative 112 divided by 2 times negative 16. And of course, that is easy enough to do on our calculator. Maybe we'll just put in another page, add a calculator. I can even be careful and do it like this, negative 112 divided by 2 times negative 16, enter. 7/2, right? I kind of want it as a decimal, right? And 7/2 is 3.5. If you're not sure about that, of course, you can always just hit second enter and it'll give you the decimal version. So that's 3.5. But that's just the time value, right? That's our x-coordinate, right? We also want to know what the maximum height is. So for that, we want h of 3.5. Now, we could certainly, and there's nothing wrong with this, plug 3.5 into this equation. I think this is a great opportunity, though, to just remind ourselves how to use the store command. So this is where I'm going to do 3.5. I'm going to hit Control var, which gives me the store command. I'm going to just put it in x because I like x better than t right now. And then what I'm going to do is I'm just going to type my function in, negative 16x squared plus 112 times x. And that then gives me the value of my function when the input is 3.5. So I've stored 3.5 in x. I then type out my function, negative 16x squared plus 112x. And its value when x is 3.5 is 196. And so that is now its peak height. Its peak height is 196 feet, and it happens at 3.5 seconds. Label it on our drawing, so I can now put a turning point there, 3.5 comma 196. That would also help us, right, in thinking about what our optimal window is. Okay. Let's keep going. Letter D. Algebraically, determine the time when the rocket reaches the ground. Label this on your graph in B. Well, the rocket is going to reach the ground when the height of the rocket is equal to 0. So, right, that implies h equals 0. So I'm looking to solve negative 16t squared plus 112t is equal to 0. And we might as well use the zero product law on this. So what I'd like you to do is pause the video now and see if you can use the zero product law to solve this particular equation. Well, as always, we want to be thinking about GCF, difference of perfect squares, trinomials, all of that. This is a binomial, so it's either difference of perfect squares or it's going to be a GCF, and it happens to be a GCF. In fact, I can actually factor out both a negative 16 and a t. All right, and I can do that because 112 is divisible by 16. And in fact, if I do 112 divided by negative 16, I get negative 7. So now I've got two things, right? I've got negative 16t is equal to 0. And I've got t minus 7 is equal to 0. Here, if I just divide by negative 16 on both sides, I'll get t equals 0. And here, if I add 7 to both sides, I'll get t equals 7. Neither one of those answers is very surprising. Now, when does it reach the ground? It reaches the ground at t equals 7. That's where it starts. And by the way, t equals 7 is no great surprise, because we knew that the parabola looked like this, and since it reaches its peak height at 3.5 seconds and it starts at ground level, it makes sense then it should reach ground level 3.5 seconds after it's reached its peak height, and that's then at 7 seconds. Okay. Maybe I should be very clear that the answer to this problem is in fact 7 seconds. Okay, so let's take a look at letter E. Observers on the top of the building can see the object when it is at a height of 80 feet or higher. Set up an inequality that models this situation and then solve for the interval of time that the observers can see the rocket. Express times to the nearest tenth of a second. Justify your answer. All right. Well, we want to be able to write down an inequality whose solution is the answer we're looking for. And what it says is that we can see the object when it is at a height of 80 feet or higher. So what we're looking for is negative 16t squared plus 112t is greater than or equal to 80. Right? So there's the inequality that models all times when the observers can see the rocket. Now, how do we solve this? Well, the easiest way to solve this, and notice it doesn't say to solve it algebraically. The easiest way to solve this is graphically. So I'd actually like you to pause the video right now and see if you can use your graphing calculator to try to solve this particular inequality, keeping in mind that we're going to express all times to the nearest tenth of a second. Pause the video now and take a few moments to do this. All right, let's do it. Well, we already know quite a bit about what's going on with this graph, right? We know that we want our x-axis to go at least to 7 and probably a little bit further, and we want our y-axis to go to at least 196, if not a little bit more. So let's bail out on this thing. Let's go into our graphing calculator. I'll go back here. I'm going to put in my function, which is negative 16x squared plus 112x. And I'm also going to put in 80 as function 2. Okay, now let's play around a little bit with our window. No zooming out or anything like that. I'm just going to go 0 to 10 on my x-axis. I think I'll have a little negative on my y-axis just so that I can see below it and I can see the x-axis. Remember, my peak height was 196. Let's see what 200 looks like. And there we go. Right, this beautiful graph, we can see the trajectory, right? The object's going up, it's coming back down. We can see that 80-foot limit right there. Now we just need to have those intersection points. So we can come in, as always, we can do analyze graph, go to intersection. Maybe I'll find that leftmost one first. So lower bound like that, upper bound there, my intersection point. Same thing, let's go analyze, intersection point, enter, enter, like this. We knew, of course, that the intersection points would be at a y value of 80. What we really needed were the times. Now this one has a time rounded to the nearest tenth of 0.8. This one has a time rounded to the nearest tenth of 6.2. Let's draw all of that on the graph now that we've got on our problem. Let's go back into full screen. And we can actually just draw, right, y equals 80. We've got an intersection point here, which is at 0.8, comma 80, rounded to the nearest tenth again. Here we've got an intersection point at 6.2, comma 80. We'd also want to label the equation of this curve, y equals negative 16t squared plus 112t. Now we still have to answer the question, right? What is the interval of time over which they can see it? Well, it's t is greater than or equal to 0.8, less than or equal to 6.2. Right? So 0.8 less than or equal to t, less than or equal to 6.2. And we can even say as shown on the graph. Right? How did we solve it? Well, we solved it graphically. The last part of the problem is pretty easy. Let's take a look at F. How long can the observers see the rocket? Well, pause the video now and see if you can answer that question. Well, what they're really asking is, how much time does that interval represent, right? And that's simple enough. We can see it from 6.2 or from 0.8 to 6.2. So if I just subtract that, the observers can see the object or the rocket for 5.4 seconds. Excellent. All right, and that's it. Now in this particular example, we were given the quadratic model, right? Here it is. Physics students know that this is going to track the rocket's trajectory and things like that. Let's take a look at one where maybe we have to generate the quadratic model. Quadratic regression. That's right, regression. It's back. So far we've done linear regression and we've done exponential regression. But you're also supposed to know how to fit a bivariate data set with a best fit parabola. And not surprisingly, it works exactly the way it does with both linear and exponential. So let's take a look. Exercise number 2. The Crazy Caramel Corn Company would like to determine how the percentage of popcorn kernels that pop depends on the temperature of the oil in which they are popped. They run an experiment where batches of popcorn are cooked at different temperatures and the percentage of kernels that are popped is recorded. The data is shown in the table below. All right, so the first thing I want you to do is kind of look at this data, and at the same time, let's take a look at letter A. Based on the data in the table, why might it make sense to try to fit this data using a quadratic function? And by the way, maybe I should even say rather than or as compared with a linear and an exponential function or exponential function. Pause the video now and see if you can answer that based on just simply what you see in the table. All right, well, notice. Right here, I've just got my x values going up by 25 degrees at a time. The percentage of popcorn kernels that are popping at this low temperature oil is very low. They start to increase, right, kind of peaking somewhere in here, and then they start to decrease again, right? So what we can see is that we have an increasing function that changes into a decreasing function, so therefore we're getting a turning point somewhere in here, right? It's clear that the data increases, the outputs increase and then decrease, which is far more like a quadratic function than either a linear or an exponential function. So something like that, right? The outputs increase and then decrease. That's probably enough, but I'm going to say thus indicating a turning point. All right, letter B. Use your calculator to find the quadratic regression equation that best fits this data. Round all coefficients to the nearest thousandth. All right, so let's do it one more time. Let's open up our calculator. Go into it. I'm going to I've already got the data in here. I can just sort of open it up. So I'm going to open a document. I've got it in this little guy, open. You've already seen me enter data before. Okay, so there's nothing new there. I've entered the temperature data in my X column, or in my column A. I've entered the percent data in column B, and I've even labeled them temp and percent, and that's going to help me a little bit later on. I didn't think that you needed to like kind of watch me do that. Now really quick, one great thing of course that calculators can do is they can produce a scatter plot for you. So if I decided right now, and I'm going to do this, I'm going to just add a page, I'm going to add a graph, okay? I'm going to go into menu, choice 3, and I'm going to put in a scatter plot. Notice it says X and Y. If I hit var right now, I have those two choices, percent and temperature. Now I want temperature actually as my X data, and in my Y data, I want percent. Now if I hit enter, I don't see anything. And the reason I don't see anything is that none of those data values, literally none of those data values fit within this window. But the graphing calculator again is kind of cool. If I hit menu and I go to window zoom, one of the options is zoom data. And if I hit that, what it will do is it will find a window that sort of fits all of the data that I have in those two lists. And it's beautiful, and it really does look, you know, maybe not perfectly parabolic, but it's pretty close. It's pretty close. All right, now that being said, let me go back to this particular one, and let's take a look at how we do quadratic regression. It's very, very similar to linear and exponential. I'm going to hit menu. I'm going to go to choice 4, which is statistics. I'm going to go to choice 1, which is stat calculations. This is where I see all of my regression. Now, the first two aren't regression, but then we have linear regression of two types. Way down here, letter A, we had exponential regression, and here, choice 6 is quadratic regression. So I hit that, and as always, I have to tell it what my X list is. Whoops, that's not what I want. I don't know how I got all the way down there. My X list is my temperature. Very important that we get these two correct, otherwise it's going to be a different relationship entirely than my percent data. Everything else is fine, and I hit enter. Okay, it says quadratic regression. If I hit the down arrow, there it actually shows me the generic model, and then it shows me the values. There's my leading coefficient, my A, there's my B, there's my C. Now, this particular problem, because these coefficients are so messy, they have to tell us what to round to, and they tell us to round to the nearest thousandth, right? And partly that's because the value of A, right, the value of A is negative 0.0039, etc., right? So if I had you round to the nearest tenth or the nearest hundredth, you know, A is basically 0 in those cases. Now, if I do round to the nearest thousandth, I get the following model. Y equals negative 0.004x squared plus 2.877x minus 427.962. One thing I discovered after I made this problem that is a little bit kind of frustrating, but I also think it's kind of a neat discussion topic that you might want to have with your classes or with your teacher, is how sensitive this model is to the rounding. All right, and you'll kind of see that. I'll point it out as we go, but we're going to continue to use this, the rounded model now, instead of like some unrounded version, which would be kind of difficult to use, quite frankly. But it's very sensitive, and in fact, rounding A even to that level kind of gives us some weird answers in a certain sense, but we're going to keep using this model from now on out. Anyway, let's use that model, right? It's simple. Nothing different from doing that, from doing our linear model or our exponential regression. Let's take a look at letter C. Based on your quadratic model in B, what temperature will produce the greatest percentage of kernels popped? Round to the nearest degree. Well, that's going to be our axis of symmetry formula, right? If we're looking for the input that gives us the turning point, then we always use x equals negative b over 2a. So what I'd like you to do is use that formula along with this particular model to figure out what temperature, right, is going to give us the sort of optimal percent of kernels popped. Go ahead and do that. All right, well, it's simple enough. I mean, it's definitely not the prettiest calculation on earth, but that ends up being negative 2.877 divided by 2 times negative 0.004. And when we just crank that out, rounded to the nearest degree, that's 360 degrees Fahrenheit. And you would definitely want to know that, right, if you are the owner of a popcorn popping company, right? Because you want to get the most kernels popped. And let's see if that seems realistic, right? It's saying in the 360 degree range, we're getting the most that we have popped. And that looks about right? Because at 350, we have 93%. At 375, we have 92%. Now remember, this is data. So this curve is not going to fit this data perfectly, especially because of the rounding, all right? And especially because of the rounding of A. The rounding of B and C are probably perfectly fine, but if we took this out a few more decimal places, we would probably really nail it down. Let's take a look now at letter D. Whoop, if we can get letter D on the screen. There we go. If a typical batch of popcorn consists of 800 kernels, how many does the Crazy Caramel Corn Company expect to pop at the optimal temperature? Now again, this is using the model. So what we need to know is, with this temperature, and the model that we have in B that you can't see anymore because it's not on the screen, what is the percent that are popped? Now this is a great place where we use store on the calculator. So what I really want is I want y, when x is equal to 360 degrees Fahrenheit, what is my y? And again, here we're going to get a little bit of a strange answer. So let me go in and add another page. I'm just going to add a calculator. And what I'm going to do is I'm going to take 360 and I'm going to store it in x. Then what I'm going to do is I'm going to type in my regression equation, negative 0.004x squared plus 2.8 7.77x minus 427.962. All right. And that's my percent, 89.358. That's my optimal percent, okay? So, you know, to the nearest percent, that's going to be 89%. Now, that's where, of course, when we look at the data, it seems a little funny, right? And it seems a little funny because if we look at the data, we've got some temperatures here where we're hitting like 93, 92%. That is all completely and utterly due to the rounding of A. If we took A out another decimal place or two, which would of course make this equation even uglier, then we would have a value that was way closer to the 93 or the 92, but we're working with this model, right? That's the model that we're using to actually do our predictions, so we're gonna stick with it, right? The whole issue of like rounding sensitivity and stuff like that is kind of a cool one in math and science, but we're not going there for right now. Now what we need is we need to know how many kernels are going to be popped, so I'm going to just find 89% of 800, and that ends up being 712. By the way, this happens all the time though. No mathematical model fits any data set typically perfectly. All right, whether it's linear regression or exponential regression. In this case, again, a lot of the reasons that we get this sort of apparent contradiction between 89% versus 93 and 92 is because of rounding the A value. All right, letter E. For a batch of popcorn to be successful, the company wants at least 85% of its kernels to pop. Write an inequality based on your model from B, whose solution represents all temperatures that would ensure a successful batch. Solve this inequality graphically to the nearest degree and show your graph below, labeling all relevant points. All right, this is very, very similar to what we did when we were trying to figure out the time interval at which the observers could see the rocket. So what I'd like you to do is write down an inequality based on that regression equation, the one where we've got all the rounded values. Try to then solve it graphically by producing an appropriate graph. Pause the video now. All right, here we go. Well, the amount or the percent popped is negative 0.004 x squared plus 2.877x minus 427.962. We want that to be greater than or equal to 85, right? At least 85%. We want that greater than or equal to 85. And it kind of makes sense, right? Because we're not going to necessarily be able to keep the oil at that optimal 360-degree temperature. So, you know, we want to get at least 85% of the kernels to pop. Now, how are we going to solve this? Well, we take our calculator out and let's see. Let me open up a new page and throw a graph in there. So what I'm going to want is negative 0.004 x squared plus 2.877x minus 427.962. That's F2. Then I'm going to want 85 and F3. And now I have to play with the window. Now, you know what's cool about this is if I go into my window, right, I know my X window is representing those temperatures. So I'll go from 0 to maybe, I don't know, 600, really overshoot everything. Y represents the percent that are popped. I'm going to include a little negative Y values there just so I can see the x-axis. And then maybe we'll put 100 as our maximum percent. And there it is. Now notice there's kind of this very limited, very small, right, temperature range at which we're going to be hitting that 85%. That's fine, right? I mean, again, what we're trying to tell the company is make sure that you keep your oil between this temperature and that temperature. And we can do that now by going into menu, analyze graph, go to my intersection. I'm sure getting tired of seeing this. Enter, enter, and we have that. Let's do it again. Analyze graph, intersection, enter, enter. Again, maybe put that up there so that we can see it better. And there we have it. And it's kind of cool because you can really visualize it, right? Any temperature that's between 300 and let's say 27 and 393, any temperature between that, we're going to be at or above the 85% mark. And so we can say to the crazy caramel corn popping company, whatever they're called, right? Keep your oil between those two temperatures if you want at least 85% of your kernels to pop. Now, in order to actually present this solution to them, right, what we would want to do is not draw a graph by hand. We'd want a nice program to draw it for us, but we're not going to do that. Just wanted to make sure I didn't have it there. A beautiful, beautiful hand-drawn graph, right? We want to graph our label our graphing window. We've got our parabola that kind of goes like that. We'd want to label it with its equation, which is y equals negative 0.004x squared. I didn't give myself nearly enough room, plus 2.887x minus 427.962. We'd also want to graph y equals 85. We want to put our intersection points in, and those are that 327, 85, rounded to the nearest whole number, and 393, 85. And then we would just say, it says write an inequality and solve it. So we could say, well, let's do any temperature that is between 327 and 393. And that's it. Bigger picture here, though, is how to model a condition using an inequality, then how to solve that inequality graphically. All right, let's wrap this up. Quadratic models are used a lot in the real world, especially you'll see them come up a ton in physics. Any kind of object that sort of flies through the air under the influence of gravity alone flies in a parabolic arc, a parabolic curve, which is really cool. Go up to a water fountain sometime, hit it and watch the water kind of go like that. Really, really neat, right? You get this parabola that's absolutely gorgeous. If I throw a ball up into the air and it comes back down, its height as a function of time is also parabolic. But then you get a lot of other things, right? Where if you've got some phenomenon that's increasing and then decreasing in a rather symmetric way, it very well may be that you could fit that data with a parabola. Apparently you got to be a little bit careful about how much you round the coefficients of that parabola, but that's something, of course, that you can kind of work out in the model if you're actually doing this in the real world. Fitting data with a quadratic model is really no different than fitting it with either an exponential or a linear model. The real key, though, is that you wouldn't want to fit the type of data set we looked at with either a line or an exponential, because those are curves that only increase or decrease. They don't increase and then decrease. All right, well, that's it for Unit 7 on quadratic functions. We're going to see them pop up here and there throughout this course. For right now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler. Until I see you again, keep thinking and keep solving problems.